Our next speaker is Farnaz Behrang from Uber, and she'll be talking to us about Dr.Fix, automatically fixing data races at industry scale. Thanks, Farnaz.
Thank you. Hi, everyone. This is Farnaz from Uber, and today I'm going to present our paper, Dr.Fix, automatically fixing data races at industry scale. So writing concurrent program is easy in Go. So you have a function call, you prefix it with Go, and it will run concurrently. So in this case, it would be an unstructured parallelism, meaning that the parent function does not wait for the child to finish. But let's say you write all of these concurrent programs, but when does the data race happen? So a data race occurs when two or more threads, or in the case of Go, we call them Go routines, concurrently access the shared memory, and at least one of those accesses is a write operation. So many of you might not know that Go is a language that is highly susceptible to concurrency bugs, including data races. So here is a real-world Go function, which comes from the Uber code base. And you don't really need to know the details of the code, but at the high level, it's a function that it fetches the balances from all the payment accounts in parallel. So there is a parallel loop here, and there is two racy access of the shared variable, which could cause a data race. Now, let's execute this program together. So let's imagine there is a user that has an Uber account with a balance of $100. And although they concurrently add two $100 values to their account, and they expect the updated balance to be $200, expect to be $300, the updated balance might end up being $200 because of the data race bug, which is going to make the user unhappy. So we have deployed a dynamic race detector that uses threat sanitizer for Go at Uber. And in the last few years, it has found more than 8,000 data races in the 100 million lines of code of the Go code base that we have. And our team has studied about 2,000 of these data races in a paper that was published in PLDI'25, which is about these different data race patterns. And so one thing we noticed over the years was that the number of races that has been detected was per day was more than the number of the races that the developers can fix. And on average, it took developers 11 days to fix each of these races. And this is mostly because application developers are not necessarily concurrency experts. Okay, so then that's when we started asking this question that can we automatically fix these data races? And so what are the challenges there? There's like a bunch of racy patterns out there. So it means that the solution space is large. Lock protection is not always the correct solution. And especially in the case of Go, it's more challenging because the Go supports both message passing and shared memory as a means of communication between the Go routines. And there has been some prior work. Most of them has been rule-based approaches that only covers a small space of the real-world problems. And with the advancement of the LLMs over the last few years, then we wanted to know if large language models were able to fix these data races. So let's say we have this threat sanitizer-based stack trace. We throw it at LLM. Would it be able to come up with the fix or not? And this is what we use as a baseline to compare our tool against. So we have this rich database of the past bugs and manual fixes that the developers have done before. And we wanted to leverage these and see if LLMs would be able to come up with more and better fixes using these patterns. So using these past boxes and the fixes that developers have done, we generated the bug embeddings and created the database of these bug embedding examples, and also used some smart search to find the good example, which is the closest matching example for the new bug that has been filed to generate more and better fixes. So basically, the two key ideas behind Dr.Fix is generating these bug embeddings and the smart search that we do. So in the next few slides, I'm going to talk about each of these ideas in more details. So let's first start with the bug embedding generator. So this is a step that we mostly do offline. And so given a curated list of the bug and fixes that we have, it extracts a pair of the racy code and the fixes and generates the concurrency skeleton for the racy code and uses that as a key in the vector database that we have, along with the pair of the buggy code and the fixed code as a value. But what is this concurrency skeleton that we use as the key in our vector database? So let me explain that to you with an example. So here again is a real-world Go program from the Uber codebase that involved in a data race. So we have a Go routine, one Go routine here and another Go routine here, and there is this air variable that is shared between the Go routines and has a racy access. So in Go, if a variable in the Go routine is used from the outer space, it uses the, it doesn't have the value of the object, but points to the reference of that variable, not the value of it, and therefore it causes the data race. So now let's see, look at the concurrency skeleton on the right side. So you can see here that we have the air variable that is renamed to the racy variable, and all of the concurrency structures in the Go, such as the Go and wait, are renamed as is, but the rest of the statements are dropped, and all of the other types, functions, and names that are not related to the concurrency are renamed as just generic names. And so to achieve that, it uses a specialized form of program slicing. And if you're more interested in the details of that, you can check out our paper. OK, so the other thing is that we use the smart search. So given this thread sanitizer-based stack trace, we want to find the candidate code locations where the data race might exist. But what are these candidate code locations? So based on our empirical findings, most of these data races have a fix that exists either in the leaf function of the stack trace, the root function, or the least common ancestor function between the parent and child Go routines in the stack trace. And these are the ones that we consider as the candidate code locations. So now that we have these candidate code locations and the vector database of the past examples, let's see how the GenAI-based fix generator uses the retrieval augmented generation to generate the fix patches. So given these candidate code locations, it generates the concurrency skeleton for them and compares them with all of those concurrency skeleton that we already generated in our offline step for all those past bug fixes to find the best matching example for that particular new bug. And this is provided along with those candidate code location to the GenAI model to generate these fix patches. And then each of them is getting validated. So we compiled it, run all of the tests with the concurrency mode, and then if there's any failure, this is fed back to the LLM, and this process is going to continue until it will come up with a validated fix, or it just times out. But let's take a look at what are these different attempts that we do with the LLM. So we have this feedback loop that, so first of all, we look into the different granularity of the code as a coding context. So basically, it operates on the function level, file level. So we have all of these build test error messages that we collect and feed it back to the LLM. And also in terms of RAG, we use not use RAG at all, using the RAG without the concurrency skeleton, and also using the RAG with the concurrency skeleton that we have generated. So with all that, if the fix generator is able to generate the validated fix, this validated fix is provided to the developers for review And if they approve the fix, then this will be landed into our code base. Okay, now I'm going to briefly talk about the impact of the Dr.Fix at Uber. So we looked into applying the Dr.Fix to the Go code base of the Uber, which contains of 100+ million lines of code. The LLM model we used was GPT-4o, and the size of the examples database that we used was 272 of the past bug fixes that we had. Then we applied that in 204 reproducible Go data races, for which the tool was able to generate fixes for 55% of them. And of those 55%, 88% of them were approved by the developers. And with that, these manual fixing times, that was 11 days per race, came down to 3 days per race. And this excludes the investigation time that the bugs are like waiting in the queue. And then we wanted to know what are these different categories that these bug fixes belong to. So we went and manually categorized them. So these are some high-level categories. So the largest category was captured by reference in Go routine that accounts for 41% of the fixes. And the examples that I showed earlier in the talk belong to this category, captured by the references. And then we had other categories for missing or incorrect synchronization, parallel test suits, capturing of the loop variable, and concurrent map or slice access. So I'm going to show now 2 examples so you guys get a better idea how these other categories look like. So this is one example that for the missing or incorrect synchronization. So on your left side, you see the code before fix. And so you see there's a for loop, there is a Go routine, and then there is this sync wait group that just uses like an add function on that. So what is sync wait group? So it's a synchronization mechanism in Go to wait for all the Go routines to finish before proceeding. And it mostly uses the atomic counters to achieve that. So in this case, what is expected that this sync wait group add we define outside the Go routine. But this is one of the classic mistakes that the developers make, and they define that inside the Go routine, which could cause the data race. And you can see on the right side the suggested fix to move that outside the Go routine. So another category, concurrent map access. So here you see a definition of a regular map in Go. And although this map has a per shard mutex-based locking mechanism, but still it could cause a data race because we have this run shard program that is run concurrently. So it iterate through the different items in the map and delete them if needed. And since this is running concurrently, so while one of the Go routines is going through that, deleting, it's possible that another Go routine does the same thing, and that could cause the data race. And in this case, there's another usage of the map as well that you can see that the values of the entries in the map get updated. Now, what is the suggested fix here is to use the synchronized map instead of the regular map in Go. And so you can see here that different usage of that map is also updated accordingly to use the just different APIs that belong to the sync map library. So next question that comes to mind is, what are the other categories of races that Dr.Fix was not able to fix? And so we manually looked into some of these past bugs that developers have been able to fix manually, but the tool was not. And then one of the top categories was fixes that belong to more than one file change, required more than one file change, or changing or reducing parallelism, changing the business logic. So there were some cases where the fix was in the external library, or some large code refactorings that the developers have done. So as you can see, for some of these categories, like changing the parallelism or changing the business logic, They might not be the easiest for the automated tool because they heavily rely on the intent of the developers, which might not be easy to extract automatically. So we also performed an ablation study to understand the contribution that each of these components that we added to the technique helped with the effectiveness of the Dr.Fix. So first of all, we wanted to know, compare the not using RAG, using a RAG but without our concurrency skeleton, and also RAG with the concurrency skeleton that we generate. So not using RAG at all, we were able to generate fixes for 47% of the data races. Then once we used the RAG, but without our concurrency skeleton, the number went up 3%. And with the concurrency skeleton, the number went up to 66%. So we also wanted to evaluate the impact of our feedback loop using different scopes and error messages. And as you can see here, using the function only, file only as just a scope or coding context that is provided LLM, or the file plus the pass failure messages is not as effective as providing the combination of all of them. So to wrap up my talk, so today I talked about the concurrency bugs, in particular data races, which are pervasive and they are hard to fix. So although Go makes it easier to write these concurrency programs, at the same time it makes it easy to create these concurrency bugs as well. And there has been some approaches in the literature, but most of these are rule-based approaches that have limited reachability. And that's why we proposed Dr.Fix, which is a GenAI plus program analysis-based technique to catalyze these data fixes. And with that, we were able to reduce the fixing time from 11 days to 3 days. And it has been deployed at Uber, and it has fixed more than 200 bugs in a span of roughly about a year. And the key ideas behind Dr.Fix is uses the bug embedding plus the smart search. And so we believe that a general idea of using the code skeletons helps make LLMs more effective for different software engineering tasks. Yeah, that's all I had, and I'd be happy to take questions.
Thank you for the interesting talk. I might have missed it, but how exactly do you match the newly found bugs with the keys in the database? Like, I don't think the skeletons will exactly match.
Right, so we generate the embedding vectors, and then we do the distance vector of those embedding vectors to find the closest match.
I see, thank you.
If you could state your name and affiliation before asking the question.
Kimi Yo, Privatskalater. So do you have any metrics on whether or not these kinds of cure-all tools like Dr.Fix, whether they lower the quality of the code base because it could make your developers more complacent, given that I don't have to write concurrent correct code anymore, and I'm just going to let this super tool find the bug for me and fix it for me automatically.
So even before we have deployed the Dr.Fix, we have these 8,000 data races that it was found in the developer's written code, right? So this was kind of the solution to help the developers fix more bugs instead of having their time relying on just manually fixing those. We provide automated solution with them. And this is in general improving the developer productivity. Let's say you help developers having IDEs or other automated tools. So this is another tool in their toolbox that they can leverage to improve their productivity.
Another question? I think we had one at the back there. No?
I'll take one at the front. Hi, I'm Marissa from University of Utah. Thank you for the talk. Can you break down the 3 days race fixing time? What goes in it?
Oh, okay. So it start when the developers start working on the tool, start working on fixing the bug from the moment they pick up that. Then, so they have like, sometimes they just write the code and stuff, and then they raise the diffs for the review, and someone reviews, then approved, and then it's landed in the code base. So from the time they start to the time it's landed in the code base.
We have time for one more question.
I'm Param from Microsoft Research. I was wondering if you have experimented with asking the developers about the bug, taking their input, maybe a couple of lines of data that they know about the code. How has that helped? Are you looking into that?
So you mean asking their opinions about the tool?
Yeah, maybe raising it as an issue, asking them for comments on that issue, or what the PR that you generated, whatever the comments were about that, and incorporating into another fix.
Right. So I think actually we did also user feedback that we reported in the paper that I didn't talk here about, but I think we had I think 3.4 out of 5 user satisfaction on the use of the tool, and then I showed that 88% of them were approved by the developers. Yeah. So we had like 12% that was not, and so in terms of the feedback that we got for the reasons that developers rejected the fixes, it was basically sometimes they wanted like better readability for the fixes that was generated. Also, they wanted to use a different approach to fix that. So, and then also, sometimes they thought it's not like the correct fix. So.
All right, let's thank Farnaz for a great talk.